Okay, so this is the third week of this semester. Yes. Okay, can you see the slide?
Yes, Dada.
Okay. So this is the first modeling for information retrieval. So basically we have 1, 2, 3, 4. So this is the first one. We will cover the following. The first one, we have to look at some of the basic concept and vocabulary that we use for defining the information model. And we look at the three models, basically four. We have the Boolean model, we have the term weighting, but it will be expanded to term frequency and inverse document frequency. So basically two. And then the last one is the vector space model. Okay, and we also from the first model to the next model, we provide reason why this model is no longer used, and then why the next model is introduced in order to overcome the problem or difficulty. Okay. So today we will cover the Boolean model and also the term weighting model. Next week we will cover the TF-IDF and also the vector space model. Okay. So let's take a look at the first one. So before we go further, we need to define what is the purpose for modeling the information retrieval. We want to define a concept or a mathematical formula that can be used to retrieve and rank the document. Basically, we need to have a framework. Okay? And the task for the framework is to how do we represent the document and then the query logically means in terms of binary 0 and 1. And then how do we define a ranking function for measuring similarity? So this function will be used to assign score to each document in relation to the given query. So given a given query, each document will be given a score how similar they are to the query that asked by the user. Okay, so these are the two main concerns when we want to model the information retrieval. Okay, so the end goal of the task is to identify and then rank the document by relevance to the user query. Okay. I saw someone coming again. No. Okay. So why modeling matters? Why do we need to do this modeling? Okay, there must be a systematic way on how do you represent the document, and then how do you actually compute the distance between the query and also the document in order to calculate or quantifying the similarity between the query and also the document. Okay, so in most cases, what we have is that the search involves uncertainty and vagueness due to the different background or due to word are used in different contexts. Okay, for example, if you are looking for this term, AI in fish farming. So it could be something to do with academic research paper or government report or commercialized AI tool for aquaculture. So there are some ambiguous or incomplete um, clue on how do we proceed, which kind of document that we want to go. And at the same time, also, since we use natural language is the language that we use to express what we want. Different people will use different term or they will express in different manner because they have different background. Each one of us will have different background. Okay, so the user may not know the right keywords in order to find the term that we have. No, to find the document that we are looking at. Okay. For instance, next semester you will be asked to find a supervisor to look for project that you will do for project one, right? So now is the best time for you to look into what topic you want to search or what topic you want to explore. So it depends on your background knowledge, what knowledge you have. So the more you read, the better search process you can have because if you have enough knowledge, then you can find the right document for you to proceed or to expand your knowledge. But if you do not have or you don't know what you are looking for, so everything looks the same to you. Okay, so different people will have different background, and thus you will have different opinion on how important is the document with respect to what you want to search for. Okay, so the model that we will look into will define how document and query are represented and how they will be compared to each other. So the query given, we have the weight or some signature on the query. So we want to compare um, the distance between the query and also the document, how similar they are, and how do we quantify this one. So we need to have this mathematical foundation on how do we decide which document are more relevant and how do we rank them. So in performing the ranking, it will transform a simple retrieval task into a graded relevance problem in which you will have certain kind of scoring to rank them. Uh, so if you compare with the database, you perform the SQL statement to find certain record. So that is the exact matching, 100% exact matching. But for information retrieval, we are looking at how they are similar. So we are looking at the degree of relevancy. How important is the document with respect to the query that we have? Okay. So for that reason, uh, this allows user to see the most likely relevant result first. So we rank them uh, based on the scoring. So the top one might be the most important document for the user with respect to the query, or might not be the most relevant. So it depends on how you key in your query. Okay. So, in looking into the IR model, basically, when we are looking at the document, we are looking at the document property. So, nowadays, people are looking at the web, right? So, based on the web, they have the text and also the link and also the multimedia and so on. Okay? But to retrieve the document, in this context, we are looking at only the text only, text form only. Okay, so we will not look into multimedia such as images, video, and audio. So if we look at the text and link, we are looking into the classic IR model. So we are looking at the Boolean, the vector, and probabilistic. Okay. So for this one, we will go further. So we will look into the set base, extended Boolean, and so on. So we will go into this direction. Okay, so of course there are so many other methods here, but we want to build a foundation, a basic foundation for you to at least know what are the model, the earlier model, and what are the most common model that they use nowadays. Okay, so remember nowadays ChatGPT is very popular, right? So ChatGPT use the same concept in information retrieval. So they call it large language model. So they use the same concept in which each document or each word will be represented as a vector of um, number that represent many things. Okay, but once you complete this course, then you will have better understanding on how ChatGPT works. Okay, so we will go into this direction. So this like just telling you there are so many methods. Okay, so similar to the course that you are taking in text mining, you will see the same thing in text mining, for example, TF-IDF. Okay, so it's okay. So in retrieval, we have this ad hoc and filtering. So what is ad hoc? Ad hoc is a one-time retrieval where the user submit a query to search a static document collection. Okay. Uh, for instance, you are looking at certain concept or certain document, and then you just type in Google. But if you don't log into the Google account, then they will not keep track what you are looking for. So this is what we call profiling. So each of the user here will try to ask the query, so they don't do profiling or they don't keep track of what your past search before. Okay, so this is used when you need information on demand for a specific purpose. You don't care about your profiling. But nowadays, we have this filtering where each user will be given a document based on the profile that they have. Okay. So if you, on a web browser, if you log in your Google account, they know what is your background. They know what are the past search that you have done. So they will narrow down the document based on the profiling that you have. So they build your profile based on your history of Google query. Okay. So this is based on a user profile. So this one adapt over time. So this is over time to user interest. Okay. So you can try this one because if you log in into the Google account and you type on certain word, it will come out differently when you log in into the account. So login and not login, you will have different set, but maybe 80% the same, but 20% different. Okay. Okay, so the information retrieval process given below. So if you have your information here, this is your information. So you key in the query here. Okay, so all the document that's stored in the database will be retrieved based on the index term that match only. Okay, so all of this document will be ranked based on the index term that match. between the query and also the document. Okay, so the main concept of IR problem is we are dealing with the problem of predicting the relevancy of the document, and um, this problem naturally embody a degree of uncertainty and vagueness. So uncertainty means there is no exact matching. It depends on what keyword you type in, or the order of word you key in, or the context on how the word is being used for searching a document. And vagueness means, um, for example, if you type bank, are you referring to um, bank, like bank account or name of a bank, or are you referring to bank, the bank of the river? Okay, river bank. So it depends on the context on how do you use the word. Okay, so to model the IR model, we will outline four terms here. So the first one is called the D. D is a set of logical view for the document in the collection. So basically, this is the framework that we have. We want to represent the document in a logical views in such a way that we can quantify the similarity between the document and the query later on. So this is your document here. And then we also have the query. So the query must be in similar representation. So we say Q is a set of logical view. So we will have Q and D here. So when we have these two, we must be able to find the distance between these two, but we need to have the function to quantify the similarity. So we need to have um, the, the F. Okay. And lastly is the ranking function. Okay. The F is the framework that we have to represent this, and also this is the ranking function that we will be using. So this is the ranking function that we will define later on. How do we compute, or how do we quantify the differences between the document and the query? Okay. Any question? So we will use this model. So each model we have the framework, and each model will have the function on how do we quantify the differences, and then based on this we can rank the document. Okay, so if you're okay, can you type number 3? Okay, so let's proceed. So now we have this model. What need to be outlined before we can perform the ranking? So we need to know some of the basic that we use. So for each document that we have, we will have the keyword or index term that will be used to represent each document that we have. So each document will consist keyword or index term. Okay, and this index term will be collected, and sometimes they call it bag of words. Okay, a bag of words that represent a document. Okay, so this document could be anything like concept or nouns or place, things, idea, and so on. Um, Basically, this like it is this is will not be counted. This is what we call the stop word. Stop word means they do not carry any meaning. Okay, so we will look like keyword, mean, and then place, role. So this is the example on how do we detect the nouns. We could also have the general form, which means that we take all of this as the token, as the token that represent the document that we have. And when we bake all of this, when we collect all of this, so this is what we call the vocabulary. So this is like your dictionary. So the set of all distinct index term. So from here, once we have collected all the unique term, then later on we will use this term to form what we call the term document matrix. Okay, this will be used to compute the ranking. Okay, so based on the knowledge that we know that each document will be represented by set of terms. Okay, so let T be the number of index term in the document collection. So if we have the keyword I, so the keyword I must be within the first and the last keyword that we have in the vocabulary. Okay, so T will be what? The number of index term, the number of unique term that we use in our framework. So if we are referring to KI refer to one of the keyword that we have in our vocabulary. Okay? So our vocabulary will be represented by this set. So K1 up to KT. So we could have KI and then KJ. So all of these will be inside here. So this is set of all distinct index term in the collection. Okay. So so once we have that representation, so for example here we have K1 up to KT. This is K1 up to KT. So we can use the binary representation to show whether that keyword exists or not exists in each of the document that we have. For example, like this, if we have T number of keyword, so we could have from 1000 up to 1111 pattern. So basically, what we will have 2 to the power of T number of different pattern that we have here. So we can use this pattern to do the matching. Okay. So each of this pattern of term co-occurrence, because term co-occurrence means what are the terms that exist at the same time for each of the document that we have. So this is what we call the term conjunctive component, term that exists at the same time in the same document. So for each document DJ or query queue, we associate a unique term conjunction component. So each one of them, for example, let me go to the next one. Here. So for, let's suppose we have this pattern. So for us to express this is just to say 1 and 0 and 0 and so on. Okay. So that means we are looking at all of this must exist for that particular document that we have. Let me go to the next one. Okay. So for example, like this, we are looking at this vocabulary. So we have 4 only. Okay. So for a document D1 containing only this, okay, the conjunctive component will be 1 and not, because this is 0, and then not 0, and then not 0. Okay, because when we say that the document containing only a keyword 1, so that basically say that we have this is 1, this is 0, this is 0, this is 0. So for us to form the conjunctive component, we have to make this expression to be true, right? So what we want to add is we want to add this n. But when we add the n, since this is false, automatically this one will become false. So we need to add this not. Okay, so not means they are not in the document. So this is what we call the conjunctive component for document 1. Okay, any question? Okay, so they use binary to represent whether that term exists in the document or not. So the way they express, so this is the logical expression of document 1. Okay. Okay, so if you go back to the previous one just now, so we want to have this n and then n. So this symbol say this is no. Cannot K2. So which means that document 1 has the following term conjunctive component, which is K1 and not K2 and not K3 and so on. So until not KT here. Okay. So for this one, we have n also, but all of them will be 1. So the final expression will be 1. Okay. So what next? So now we want to know what kind of pattern that looks similar to each other. Okay, so we want to look at another term here. But before we proceed to that one, we will look into, because from here, then we can construct the term document matrix. The term document matrix will outline the term that exists in each of the document that we have. So for example, here, the occurrence of term K1 in a document DJ establish a relation between K1 and DJ. So for example, like this is your document, D1 and D2, and this is the keyword. So the value that we have here, for example, this is the keyword for, no, this is the symbol, or what we call it, the weighting, for keyword 1 in document 1. So this is the weighting. Weighting refer to pemberat lah, or in this case we use binary kan, so it could be 1 or 0. Okay, so this one indicate whether key 1 exists in document 2 or not. So this one, key 2 exists in document 2 or not. So this is what we call term document matrix. Okay, so we will use this format. So So basically we are translating this one into a matrix. Okay, so yang here is your document. So we just transpose your matrix. Okay. Okay. So, but before that, the framework that we use to represent document will be this, the term document matrix. So this is the framework that we'll be using. Okay. But for us to tokenize all the terms, for example, let's go back. Okay, for us to be able to get this keyword 1, 2, 3, because this keyword 1, 2, 3, we expect all this keyword coming from all the document that we have here. So we need to tokenize all the content of the document that we have here so that we can list them out here. Okay. So the process is here. So when you have the document that we have, we know the structure. So based on the structure that we have, we will remove all the spacing, and then we will remove all the stopword. Stopword is list of term that does not carry any meaning. For example, if we assume this one as one document, so this one carry no meaning of because they exist too many times in the document. In each of in all of the document, you will have this of and so on. So we remove this, we remove this, we remove this, and this. Okay, and in stemming we remove this. So that means we finding the root of the word. For example, play, playing, played, plays. So all of this one will be counted as play only. So that is stemming. We remove all the symbol and we find only the root word of the token that we have. Okay, so this one is okay. Here we remove all the stop word. Over here we detect all the nouns here, and then the stemming here just produce only one, but you will be counted this one as 3 because 3 time exists, but using the one root word only. Then this one will be put in the vocabulary. So this is the word that we will be used here. Okay. So this one will be your first programming. So I will post the assignment later on. Is to read the file and then tokenize them. So you need to be able to put them in this context, or at least list all the term that they have, and then which document has what term that it should be. Okay. So any question? Okay, if you okay, can you type number 2? Okay, so now we just now we talk about this kan this logical expression. So they have come up with this, and then at the same time they introduce this Boolean model, because Boolean referring to true, false, yes, no, 1 and 0 only. Okay, so this is the lightest model that we have, because we just have to keep track exists or not exists, but we do not count how many times they exist. We just say how many times they not. We just want to know whether they exist or not exist only. Okay, so the Boolean model is a simple model based on set theory and Boolean algebra. So so basically, this is similar to your SQL, in which you SQL statement in database, you are looking for exact matching, right? So similar to this, since we are using exist or not exist, we are looking into exact matching. Okay, so for example, if we have query like this, so basically we are looking for keyword A and keyword B, or not keyword C. Okay, so in the Boolean model, we use 0 and 1 only. So 0 if not exists, 1 if they exist. Okay, so if you have query, so we will use the knowledge that we have before. We will use the term conjunctive component. Okay, so the term conjunctive component will be in this format. Okay, and we will have this vocabulary A, B, C. Okay, so what we want to know is what are the pattern of A, B, C that will give you this expression to be true. Okay, so for example, this is N, right? So this is 1. So either this must be 1 for this expression to be true. Okay, so you will have 1, 1, 1, you will get true, or 1, 1, 0 to be true, and then 1, 0, 0 to have this expression to be true. So basically, we have three pattern that can say that is similar in terms of the final result of your logical expression. Okay, so for that reason, we will say, okay, either we have this pattern, or this pattern, or this pattern, all of them referring to the same document. Okay, so this is what we call the disjunctive normal form. Okay, where we have a few expression that will give you the same result. Okay, so from here, let me erase the rest first. So from here, we are looking at this is your query. So your query normally in the conjunctive component, only one expression. Okay, but you will have to convert them into disjunctive normal form in order to cover those patterns that will give you similar results. So from conjunctive normal form into disjunctive normal form. Okay. So when do you use this? You use this when you want to match with your query. So you just finding the pattern which is similar, exact matching. Okay. So for example, like this, if we have three keyword K, KB, and KC, so when we are here, so that means keyword A exists, but not B and C. Okay, so for this one is keyword A and B exists, but not C. So this one, all keyword exists. So A should be what? So we have 0, 1, 0. Okay, and B would be 0, 0, 1. Right? So these are the pattern that we are looking. So we just match with um, the document. Okay, so what we want to know here is the full process. So given the vocabulary that we have, so we have this vocabulary. Okay, so we have A, B, C, D, and then we have this document that contain only term A, B, C only. So this is the representation for the document J. So we have 1110. Okay. So if we have a query which is similar like previously, so we have A, B, C, but in the query it doesn't mention about D. There is no mention about D, right? But your document consists of 1110, which for this one, your KD is not inside the document DJ. Okay. So since your query only specify A, B, C, so basically you don't care about whether that document consists of keyword D or not. You just don't care. So basically what you focus is only these three. So if you have 0 or 1, you don't care, you still accept. Okay, and this is for the second one. So you don't care about the KD here. As long as you have 110, 110, you still have, because if you have 110, so this is one, so this is not 0, you become 1, so the whole thing will become true. Okay, so this the 3 bits coming from here just now. So this one. Okay. So this is the representation of the query. This is when you have this document, your query must match with the representation of the document that we have. Why? Because based on this, then we can do matching. So we must have the same length of binary that we have. Okay, for this one we have 100, 100, but we don't care about the D here. Okay, understand? Boleh. Okay, so basically what we have is when we have this query and we have this 4 keyword, but your query do not have the keyword KD, do not have the KD. So we will apply the same result before, but we just add this. Okay, so this 2 will cover pattern 111, and you don't care about the KD 0 or 1. Okay. Okay, so let's do some exercise here. Okay, for example, like this is your query. You need to have keyword A and B or C. So how do you convert this into disjunctive normal form? So basically, you are combining this and this. So you will have A and B or A and C. So you have 2 components here. Okay, so these are the expression that you will have. Okay, you can stop me if you don't understand or you stuck here. Okay, for this one, So we have two or inside. So we have two here. Okay. So how do we differentiate? For the disjunctive normal form, you will combine them using the or operator. Okay. So for this one, we just combine this. Sorry. Let me use different color. So basically, we are looking at that. So this is A and C, and then A and D, and then B, C, and then B. Okay, so you will have. Okay, so this is the disjunctive normal form. So remember that. How do you know that you are in the disjunctive normal form? You use O. Okay, we have another situation here. So this is we have not here. Okay, so your query is in this form, but this one is already in disjunctive normal form because we have this. So I don't need to convert anymore. So that is your, yeah. So that is the first clause and second clause. Okay, so how do you know that you are in the disjunctive normal form? You have the or operator that combine the same number of bits. Okay. If you want to check also is that whether you get the right uh, disjunctive normal form, you cannot have this is 2 and then the other one is 3. So you cannot have A and C and D. So you must have equal length. Okay. Okay, next one. Mixing parentheses and not query. So we have this. So this is not in disjunctive normal form. Okay. So we are combining this and this, or this and this, or this, or and this. So we have 4 components here. Okay. Okay. These 3 groups of distributed. So we have 3 here. Let me erase first. Oh. So we have n, right? But inside here we have O. So we just combine A, C, E. So we have 3, 3, 3. So we have to follow the order so that we don't forget. So this is A, C, and F. And then A, D, and E. Okay. And so on. So you will have 8 number of component here. Okay. Okay, we also have this O. Okay. So since we have O, so they are all in the DNF already. So we have individual A, B, C. Okay. And this is the example that we have. Okay. This is the same clause because we cannot expand them. Only one representation because we must have A, B, and not C. So there is no clause here. Okay. Example of don't care is the one that we have just now. So we have all this. We have the vocabulary we have A, B, C, D, but your query only consists of A, B, C. Okay, so for us to expand this one, so we just A and B or A and C. Okay. Okay. Any question? Okay. What is the purpose of converting conjunctive normal form into disjunctive normal form? Do you have any idea? I go back here lah, so that you can jawab. Hmm. Okay, what is the main reason why we need to convert into this? This is your conjunctive normal form. We convert into here. Why? Okay, if we convert this one, can you help me to convert this into disjunctive normal form? Okay, you have this format. Okay. So if if you have this query, so we have KA and KB, right? And then we have KA and not KC. Okay. So meaning that we could have this or this. So if we have this vocabulary, basically we need to have one and one, right? So we don't care about C. So we have one, one, one. Okay. So if we have this KA and not C, so that means we need to have um, 1, 0, because B is not specified here. So we can have 1, 1, and then this one must be what? 0. Okay. So this is similar. So this one will be here. And then this one is here. And this one is here. Okay. So by having this disjunctive normal form, we are actually finding the pattern that will match the query. So these are the pattern that will match the query that we have. This is based on the Boolean model. Okay. So you understand now why we need to convert into this disjunctive normal form. So basically what we have here is all the pattern that you are looking at. So it depends on your vocabulary. You will build a pattern and then you just match the pattern with the document that we have. Okay. Okay. So now, so since we know already how to expand from the conjunctive normal form into disjunctive normal form, so we can use this pattern to do the matching, right? So the similarity of document DJ to the query Q is defined as if um, the value is 1 if there exists a conjunctive query such that the conjunctive query Q is similar to the conjunctive document DJ. So basically, we are looking the exact matching only. So for example, like this, we go back here. For example, like here. So if we have this document this keyword A, B, C, D, and we have this document. So if we have this query, so all the pattern that match with this will be true. So this one. So since they're matching, so you have the value 1. So this is all the pattern that can be generated based on the query that we have here. And this is the pattern for the document J. So what we need to do is we want to see if there is any matching of this. So if they are matching, then we say 1. They are similar. Okay, so very straightforward. Okay, but the problem is you cannot do ranking because you only say the document is relevant because that document consists some of the term that specified by, not some, all of them. We say the document is similar to that query because all the term that specified by the query can be matched into the content of the document. Okay. So for example, like this, so we have the vocabulary A, B, C. So if document 1 has this 110, document 2 101, and then document 3 is 011. So if you have this query, so the query is 110, right? And then 111 because we have this A, this is B, and then this is C. So this is coming from here, but we don't care about the C. Okay, so which one is okay? So this query, either this pattern or this pattern will be considered as similar. So which is document 1 only. Okay, so this is similar to document 1. But the problem with this is that we cannot do the what we call it, the ranking. So because if document 2 match, they also say similarity is 1 here. There is no differences between the D1 matching with the query and D2 matching with the query. Okay, so we cannot do ranking. Okay, so for that, the Boolean model here cannot accommodate this one. No notion of partial matching, which means that you have to have full matching of all your word that you have. Okay, so this is similar to your database exact matching. You cannot do partial matching and you cannot do ranking because at the end you will get 1 or 0 only. 1 means the document match with all the keyword. 0 means does not match. Okay, and all of them must be translated into Boolean expression, um, which is difficult, troublesome, and the Boolean query formulated by the user are most often too simplistic. So you have one and one or zero. Okay, so the model frequently return either too few or too many document. Okay, too few means not matching, and too many means all of the document matching. Okay, so for that reason, they say, okay, why not we look into the frequency of each of the word that we have in the document to be the weight, how important is the word with respect to the content of the document itself. So they introduce, okay, this is for you guys. Um, you, you want to do it for 10 minutes? Okay, so I let you do it for 10 minutes. So that means one question, 2 minutes. Masih dua orang lagi lobby, kasihan. Okay, so I give you 10 minutes to look into this. Okay, so I have the answer here, but I will let you to go through later on. I will share the slide later on. Okay, we will continue for a while for the next one. Um, just a few more slides. Okay, these are the answer. Don't worry about this. You'll get this one when you download. Okay, so the problem with the previous one is that they cannot do uh, partial matching and they cannot do ranking. Okay, so for that reason, they say, okay, why not we count the number of time the term exists in the document instead of only using binary. Okay, so they introduced this what we call term weighting model. Okay, so for the term weighting model, the terms of a document are not equally useful. So some of them are not carry any meaning, so we throw them away. Some of them exist so many times, so that means they are very important. So we will look into that. So what happened is that we will look into the frequency of the term in order to evaluate how important is the keyword with respect to the document. But if that word exists in all of the document, so meaning that the word is not important because we cannot use the word that exists in all of the document to differentiate the document. Okay, so for instance, this one I pick one here. So if I look at this one, right? So these two terms, we can say that all document will have this of and end, right? So we cannot use this term to differentiate the document. So this one, that's why we call it stop words because they carry no meaning. Okay, so for that reason we have to remove them. We only count the one that are nouns, keyword. Okay, so to characterize the term, the level of importance for each of the term, we will introduce the weight. Okay, so the weight will no longer be 0, 1, so but instead greater than 0. So we look into the term frequency. So this one is referring to keyword, the weight of the keyword I in document J. Okay. So if keyword I does not appear in document J, so it will be 0. So otherwise, it will be some number that quantify how important is the index term key I for describing the content of document DJ. Okay, so we will use the term frequency. How many times they occur in the document. Okay, so we will use this term frequency to compute the ranking of the document, and now we can do partial matching. Okay, so we no longer use true and false. We are looking at the weight of individual term in describing the document that we have. Okay. So for keyword that we have in the vocabulary here, so each of the keyword will have the weight with respect to the document that we have. So we will have document DJ and we have the keyword I. So the weight I and J referring to the weight of the keyword I in document J. Okay. So when we say we have the weight of the keyword, so we will have a document. So this is a vector that represent the weight of individual keyword that we have in the document. So for example, like this one, this is in document DJ. So for keyword 1, what is the weight? And keyword 2, what is the weight? And so on until we have keyword T. So all of them are in document J. So that's why we use this vector to represent individual document. Okay. So with the same weight that we have here, we can redo the term and document matrix. So previously we used binary, now we use the weight that we have. So the weight Wij can be computed using the frequency of occurrence. So we just count the number of times they exist. So we also have this, what we call it, the total frequency of occurrence for keyword I. And that is the end here. So this is for all the document that we have. We also compute how many times the keyword I exists in all of the document. So we have this capital letter F. The total time or the frequency of the term exists in all of the document. Okay, let me show you some example. Okay, for example, we have this 4 document, 1, 2, 3, 1, 2, 3, 4. Okay, so over here we are looking at frequency of do in the document 1. So the do here exists only 2 times. Okay, the frequency of do in document 2, 0. Okay, but if we do the total frequency of do for all the document, so basically we are adding up this to become 8 lah. So this is basically the total number of occurrence for keyword do in all of the document that we have. Okay, and the small letter here refer to the number of document consisting the keyword do. So which is 3. 1, 2, and 3. Okay. Okay. So now let's take a look at this one, this example. Okay. So what we want to have is we want to have this framework. So based on the previous slide here, we know how to find the frequency, right? So we want to build this term frequency matrix based on the document that we have. So the first thing that you need to do is we need to extract the unique term that we have. Okay, so we will have all these terms. So basically this vocabulary consists of all the unique term that we have from here. But we remove all the punctuation. Okay, and we convert the capital letter to become small letter. Okay, bear in mind that in this example, we treat them as individual term. Okay, but we do not remove the stopword. Okay, this is just to give you an example on how do we convert this document into the term frequency matrix. Okay, so we extract all the vocabulary, unique terms, and then we have a total of 14 terms here. Okay, so this keyword will be listed here. So we have all 14 here. And we have document 1, document 2, and document 3, and document 4. Okay. So step 2 is to count how many times they exist. So we have this. Okay. So this is what we call the term document frequency matrix. Okay, from here we can do the next move. Okay, but as you look at this term document matrix, is that each one of them listed individually. So that means we say term number one and term number two has nothing to do with each other. But in reality, we have two terms that always come together. For example, computer science, computer network, software engineering, artificial intelligence. So all of these terms always come together. So how do we capture this? So we have this what we call the term correlation matrix. Okay, so term correlation matrix. So basically, this one will capture the dependency between two terms that we have in your uh, document. Okay, so we will look into how do we capture this by looking at the weight that we have for um, this, the weight for keyword I, and the weight of another keyword in the same document. So, for example, this is A, the weight for term A. This is the weight for term B. Okay, so we want to know whether um, if the weight for each of these will tell they are always together or no. Okay, so so this is what I mentioned just now. Like for computer network, they always come together. So how do we capture this? How do we extract this from the term document metrics that we have? So what we need to do is we need to construct this term correlation matrix. Right? So based on this, the term correlation matrix, basically we are using one matrix, which is the term frequency, the term document matrix, and then we multiply that one with the transpose of the same matrix that we have. So for example, if we have this term document matrix, so the term correlation matrix can be obtained by multiplying the term document matrix with the transpose of the same matrix. Okay, so the individual weight that we have here, simply saying that if the weight is high, that means there is a high correlation between term U and term V here, because we have this calculation. So this is the weight for term U in document J times term V in document J. So if both are high, so that means they both occur in the same document many times. So that means they are correlated to each other. Okay. So the higher is the value here, the stronger is the correlation. Okay. So let me show you the example here. So this is our key term document matrix. So we transpose them. So row become column, column become row. So we have this. So this is basically the same, but we transpose them, and then we multiply them. So basically we are looking at this, this times this. So the weight 1 times weight 1 times plus the weight 1 2 so here, and then you redo again. Let me erase that one. So the second one is this multiply with this. Okay, so you have this one. and then this multiply with this one, you get this. Okay, so this is your term correlation matrix. Okay, so if the value here is high, so that means K1 is highly correlated with K2. Of course, we don't consider this because K1 and K1, they always come together. So we remove this lah. So we only looking at this and this and this. Okay, so let me give you one example. So so this is not the binary. I just put a simple number here, 1 and 0. So so this is your original term document matrix. We transpose them into another matrix. So we will do the term correlation matrix by multiplying this with that. So that is here, but we don't care here. So what we want to do is we want to compute the second one, which is K1 with K2. Okay, so that one will be here. So 1 times 0 and 0 times 1. Then you repeat again for this and so on. So at the end of the calculation, you will get the term correlation matrix. So we're only looking at the highest value. High value means they are highly correlated. So over here, we can conclude that we have K3 and K4 are highly correlated. So this is how we capture the mutual dependency between two keywords in your document, same document. Okay. Okay. So if you're still there, can you type number 7? Cheng Wei Jian baru masuk. It's okay. Okay, so since this is a recorded session, you can look into the lecture if you join in late. Okay, let me stop this one.